Chinemerem is a master's student in the Energy and Earth Resources program and a research assistant in the Gulf Coast Carbon Center. A research blurb that explains Chinemerem's work is that there are many years of experience with carbon capture and storage, but planned injection rates of projects currently in development are 1 to 2 orders of magnitude larger than previous projects. Ensuring accurate predictions of reservoir performance needs new calibration. So with that, let's get started.
Hi, thanks, Makela. Today I'll be presenting part of my research, and I've titled this talk on calibrating performance predictions for large-scale injection. So the urgent need to mitigate the impact of climate change has led to the growth of technologies such as the carbon capture and storage technology. As you can see, the chart on the left shows the capacity of commercial facility pipeline. On the y-axis, we have the capacity in metric ton per annum of CO2. And on the x-axis, we have the year. The colors basically show the stages each of these facilities, what stage they are currently in. The green one shows let me put on this. The green one shows the facilities that are still in early development. The sky blue one shows facilities that are in advanced development. The light blue shows facilities that are in construction, while the dark blue or the normal blue color shows the facilities that are currently in operation. The map on the right shows focuses on North America, and it basically shows where each of these projects are located in. And as you can see, we've had significant, or should I say, exponential growth, within the past number of years. And these are largely because of new projects that are being added, that are either under construction or they are in early development. So to focus on the capture side, this chart here basically focuses on the capture capacity of projects that are either in construction or in development. And you can see the years on the right, on the y-axis, and the capacity in metric ton per annum of CO2 on the x-axis. So the key thing to note here is that the capture side, like it's growing, and it's growing exponentially. Luckily, we have as the capture side is growing, we also have plant storage growing also, and it's growing like rapidly. This map here shows is from the Clean Air Task Force, and it basically focuses on the Gulf Coast region, and it shows some of these projects. The bubbles represent the capture capacity of some of this project, which directly translate to the storage capacity of these projects also. It's important to mention that this map has been filtered to focus only on projects that are dedicated to saline storage, which is what the focus of this talk is going to be about. So while we have a lot of experience with CO2 injection, some of the industry has a lot of experience with injecting CO2 into the subsurface, either for EER or for demonstration purposes, pilot projects. There are quite a number of them out there, but the growth that we've just seen, demonstrate that companies are looking to inject high volumes. And when I say high volume, I mean like 10 times or more than 10 times what we've seen. The chart, the plot we saw earlier basically shows you some of those bubbles represent like projects that are targeting 2 to 4 megatons per year, and some of them are planning to or hoping to sequester about over 100 megaton, in the lifetime of those projects. And the problem is that while we have experience, with injection of CO2 into the software, we don't really have a lot of experience, or we don't have a lot of history with injecting large volume in a short period of time. So there needs to be a certain way for us to calibrate performance predictions, to know if some of these predictions that have been made for some of these projects, if they are even realistic. And to do that, I have basically analyzed saltwater injection data in the Texas Gulf Coast. The map here shows, how those wells are distributed across the whole of Texas Gulf Coast. And we have about 8,348 wells, and this has been filtered to focus on wells that are injecting into non-producing interval, which means they are not used for EER. They are not used for EER or improving oil or gas production. It's basically filtered to select projects that are, disposing this saltwater that are being produced. So yeah, we have analyzed about 8,348 wells, and you can see how they are spread across. Analyzing this data, you find out that some of this data, it's actually, typically not what you want them to be. There are a lot of issues with this data, and as you can see on this this slide, we have a typical example of, what we've done to basically either like adjust volume and rate data, or eliminate some of those wells with bad volume and rate data. And on the left here, we have volume versus year, and it's basically showing you a typical example of, a well with a bad volume data. And for any well, like you have to go through all the wells basically to look at what they are, how the trend looks like. And for any well like this, we basically eliminate them. And while for any well that looks more realistic, as what we have on the right, we consider them or take them forward for our further analysis. And we also have issues with rate. As you can see, this slide shows the rate versus year, and on the left we have rate in barrel per day. And you can see for this sample well we have here, there's a big spike in, say, around 2008. Obviously this is not realistic, and when you go ahead and do your analysis with this data, it's going to give you some unrealistic result. So basically what I do is to correct this by not eliminating this particular well, but replacing this spike with the average of this other the rate that we observed in the other years, and that results to what we have on the right. So having done that, and filtered, this volume and rate data, we have, out of 8,348 wells, we have about 4,805 wells with, we deem to have good volume and rate data. And the key thing here is just, note that they are still distributed, evenly across the whole of the Texas Gulf Coast. So having, done the quality checks and, selected wells with good volume and rate data, it's important for us to do a regional assessment to understand, what performance of saltwater looks like in the Texas Gulf Coast. This plot here shows volume versus year, and on the left we have volume raised to power of 7. That is 5 times 7 raised to power 7 basically. just to mention that. And we have the year on the x-axis, and you can see the trend of water injection from 1990 to December 2020. And this is basically filtered, based on, when the data is available digitally from the Railroad Commission and to 2020. So you can see how the trend, how basically the volume or the volume changes with time. And we've made this plot has been made using the 4,805 wells that we selected to have good volume data. During this 30-year period, a total of 20 billion barrels, approximately 20 billion barrels of saltwater has been injected in the Texas Gulf Coast, and this approximately translates to 2.3 gigaton of CO2 equivalent in reservoir condition. I mean, this is big volume. One may ask where they're injecting this saltwater, but where is it? Where are they injecting into? What are the target formation for this injection? And this plot here shows the total injected liquid in barrel raised to the power of 9 versus the injection target on the x-axis. And it's important to know that we have about 4,001 wells instead of 4,805 wells, because not all the wells have their injection target reported. So you can see that the Oligocene, Miocene, Woodbine, Wilcox, which are traditionally known as good formations for injection projects, have the highest volume. But we also see the lower Cretaceous here with also coming up with high volume. And this initially was not expected, but this is what the data tells us, and it's important to note that and keep that in mind. Why volume is a good indicator of performance to some extent, it's quite not robust. So it's important to take into consideration, the impact of pressure, and that is where we basically go ahead and calculate the injectivity index, and this is basically simply a measure of how much fluid we can inject through a well at a given pressure differential, and this is how it's expressed. And we have Q, which is the average injection rate, and the PF is the reference formation pressure. For this case, I've assumed it to be hydrostatic, and the PBH is the maximum bottom hole fluorine pressure, while the J is the injectivity index in barrel per day per PSI. So we looked at the volume data, but also the pressure data is even worse, right? And so we also need to do some quality checks on the pressure data to select wells that are actually have good pressure data in order to have better result, basically. And these are some of the steps that I took or implemented, to be able to select wells that have good pressure data. And out of this, the 4,001 wells that we saw earlier, only about 600 of these wells passed this test. So to calculate injectivity index, we need to get the bottom pressure, bottom flowing pressure, but what we have, what we got from the Railroad Commission is the wellhead pressure. So we need to translate the wellhead pressure to the bottom flowing pressure, and we do that using the Darcy-Weisbach equation, which is shown here. So having selected, those 600 wells, we need to, I went ahead to make the plot so we can see how the wells are distributed. And you can know that we don't have 600 wells here. we have 593 wells, and that's because to convert the wellhead pressure to the bottom pressure, we also require some completion information, and 7 of those 600 wells don't have the required data to do that. But the key thing to still note here is that we still have some kind of even distribution of data across the Texas Gulf Coast, and that's one thing to keep in mind. So we go ahead and calculate make a plot of the distribution of the injectivity index, and we have on the y-axis the probability density. We have on the x-axis the injectivity index in barrel per day per psi, and this is in log scale, and you can see we have quite a number of high performing high injectivity wells, but also have a number of low injectivity wells. To be able to understand, what how formations are performing, the ability of, because we want to understand how good is the formation in terms of receiving fluid. But to do that, we need to normalize the injectivity index, and what that basically means is that we divide what we saw on the previous slide by the perforation interval. And the resolution of the perforation, the completion data that we have, it's low. So we have, we don't really have good resolution in terms of when it comes to the completion data. So what I've done is to select wells with perforation less than 100, perforation interval less than 100 feet, to make, to get a more realistic result. And out of those 593 wells, we have about 443 wells with perforation interval less than 100 feet, and that is, what goes into this plot. And you can see the trend is still similar. We have normalized injectivity index on the x-axis, the probability density on the y-axis, and this is in barrel per day per psi per foot. And you can still see that we have a number of wells with high injectivity and others with low injectivity. So the performance is, it varies across the entire Texas Gulf Coast. So while we've seen how each of those formations were performing in terms of volume, it's important to also understand how they are performing in terms of injectivity, right? To know, okay, those ones that we mentioned as good formation, what do they look like when we make the normalized injectivity plot? And this is a box and swarm plot, and I have included the swarm plot here just to draw attention to the number of wells in each of those formations, because it's not evenly distributed. So ideally, when you have a good well, a good formation with low number of wells, it's not better than, it's really better than maybe a good formation with a higher number of wells. So just to draw attention to that, on the y-axis we have the normalized injectivity index. On the x-axis we have the group, and as you can see, the Miocene and Oligocene Wilcox lower Cretaceous have some really high injectivity wells, and they have, compared to the other formations like Jackson or Claiborne, they have more wells also. So it's, we have more, higher information about, how these formations are performing in terms of injectivity. And when you zoom in, you can see, what this box plot actually what they actually look like. And you can see the Miocene is really good with large number of data, compared to the other wells. Same as the Oligocene, the lower Cretaceous, the Woodbine, and the Wilcox, and even these other formations, Jackson, Claiborne. But compared to this other formation that I mentioned earlier, they have low number of wells. So what if we have more wells, injecting equivalent number of wells, injecting all this formation? How will this other formation that seems to be high, perform? So the number of wells kind of give you some, confidence in terms of, because you have a Oligocene with good showing good normalized injectivity and large number of wells, it's fairly better than the Jackson with sparse, with low number of wells. So while we understand, we've understood like how each of these formations are performing in terms of volume and injectivity. There's also some kind of need to conduct a local assessment. So we move from regional assessment to local assessment, and I'm going to show like one of my case studies and for this local assessment. What I have here is what I call the Edwards injection trend, and as you saw earlier, the lower Cretaceous was a bit of surprise to us. As you didn't really expect such large volume to be going to the lower Cretaceous, and many companies actually trying putting out CCS projects, carbon capture and storage projects out there are focusing more on the known formation of Oligocene, Miocene formation. So it's important. It was important for me to look into the lower Cretaceous to understand what is actually going there. So that was my first stop. So I'm going to show this trend, which I call the Edwards injection trend, and if you can see here, it's circled in red, and it basically shows you where this trend is located, and I'll have a closer look at it in a minute. The red color indicates show wells that are injecting above 20 million barrels, and the blue one show wells that are injecting above 1 million barrel but less than 20 million barrel, while the yellow dots show wells that are injecting below 1 million barrel. Again, the key thing here is that the performance varies. It's evenly distributed across the Texas Gulf Coast. Just to emphasize why I've also picked the trend you saw earlier. This map here shows emission sources across the entire Texas Gulf Coast, and you can see that there are a lot of emission sources closer to the coast, which is where most of the companies are planning their CCS projects. But we also have a lot of hard to abate emission sources up deep Texas Gulf Coast. As you can see, some of there you have a lot of cement plants in this location, and for most of the company, they will need to maybe build large pipelines to be able to transport the CO2 from these locations to the where they have their injection projects going on. So what if we can find a good storage location in this area, and that would basically limit or make some of these CCS projects even more attractive, as we can find local storage in these locations. So this is a closer look of the Edwards injection trend, and you can see the circle that I had earlier, and you can see what they look like. We have a lot of red dots in this trend, and that basically shows you that there are a lot of really good performing wells in terms of volume in this Edwards trend. So while we've looked at the what the trend looks like, it's also important to understand to get a bit of a geologic overview of this location. And this map here shows the Edwards trend, and it also shows the faults. The yellow line show the faults, and as you can see, there are a lot of faults in this location, right? And one can easily assume that this trend, this formation, or this Edwards trend has a lot of wells. It's kind of has a close boundary condition, and it's important to know that why I call this the Edwards trend is because these wells are actually injecting into the Edwards formation, the lower Cretaceous. The black line shows the 10,000 milligram per liter line, and according to policy, you're not allowed to inject into formation with less than 10,000 ppm milligram per liter. basically, and so it's important for us, it was important for us to consider, that to see where our location falls in that. In case someone decides to explore that location for CO2 injection, and you can see that it falls well above the 10,000 line. The red one is the 1,000 milligram per liter line. So again, the key thing I'm trying to point out in this slide is that, lots of faults in this location. What if this location has a closed boundary condition? So having gotten a brief overview of what the trend looks like, we went ahead to make a cross section of this trend, and you can see this is running from north to south, and you can see the Edwards formation highlighted here, and you can see some of the perforation zones. There's a bit of uncertainty in terms of the thickness of the Edwards, at least in our data set. It's also important to note that the thickness of Edwards, from literature, from north to south, you can get up to 350 meters from thick towards the southern part. So there's a bit of uncertainty based on the log data that we got, and you can see that some of these logs are not, don't really extend to some extent. So to be able to calibrate performance, there are two scenarios that I considered for this study, and one is to take, in terms of thickness, to take the top of Edwards and the bottom, the location which we call which I call the perforation zone 2, basically, which kind of spreads across this way, and that is how we were able to come up with the first average thickness of 55 meters. The porosity was also gotten from the log, the Diffie and Enfi log, and we have a porosity about 28%, which is pretty consistent with what we also have in literature. And the average permeability for this formation was gotten from literature, from Galloway's work in 1983. And this formation is said to have an average, in this particular field, the lowland field, is said to have an average thickness of 200 millidarcy. So as I said, there's a bit of uncertainty in thickness data, and so we also considered another scenario, whereby the thickness is from the top of the Edwards to the bottom of the PEF zone 3, right? And why for this wells without any perforation data in this region, basically take the bottom to be the where we have the base where we have data on. So I'm using that. We have an average thickness of 101 meter, and permeability stays the same, porosity stays the same. Just to, I've done it just to acknowledge the uncertainty we have in the data. So now we're going to the model calibration. So, we have an initial pressure for the Edwards, initial average pressure, which, as I said, was assumed to be, we assumed that to be hydrostatic. So basically we calculate the hydrostatic for each of those, the average depth of each of those wells, and we get this pressure you see here in megapascal. We have a temperature using the temperature gradient that we in the temperature gradient in the Texas Gulf Coast. So the first case is we use a thickness of 55 meters, salinity of 0.15 mole per kilogram, porosity of 28%, permeability of 200 millidarcy, and rock compressibility of 1.71 e to the minus 10. And this is a carbonate formation, just to point that out. Then we set the boundary condition to be closed, and we run the simulation for 372 months. Injection well reduced to be 0.73. So for this particular case, we ran the simulation, and the model basically did not come up with any result. Because of and that's mainly because the volume was large. The pressure buildup was so much, so it's, it's so much that the model couldn't run. So, initial assumption that this place might be under a closed boundary condition, maybe it's wrong. So we went ahead to open up the boundary condition, so set the same conditions, basically, thickness the same, permeability the same, but we then open up the boundary condition, and we got some result. And as you can see, we have a result. Basically, this shows you the bottom hole pressure that was observed, the maximum bottom hole pressure that was observed during injection. And this model, this tool right here is the Easy tool, which we have in-house of the Gulf Coast Carbon Center, and this is basically a single phase model. So it's basically designed to simulate saltwater injection. So you can see the maximum bottom pressure here, which is 28 to 29 megapascal, and this is way above what is reported, which is around 12.4 megapascal. So there has to be an issue, because if Edwards formation is taking so much volume, something must be wrong. So again, this is like what I call the case B1. So we have another scenario where, I have what I call the case B2. And for this scenario, it's basically, moving from a thickness of 55 meter to a thickness of 101 meter, and every other thing stays the same. Boundary condition in this case is open, and we have a result, and this result shows a maximum bottom pressure of about 20 megapascal. It's still way higher than what we have reported. So something must really be going on. In order to understand what's going on, I run another case, which is called the case C1, and this kind of is consistent with the case B1, which has a thickness of 55 meter. So we then, changed the permeability up to, it had to be changed up to 1250 millidarcy to be able to get the results we have. So we have the maximum bottom pressure to be around 12 megapascal, which is kind of now consistent with what we have in reported, what we have as reported in the data. So it kind of gives us a bit of information of what's going on in the Edwards formation, which is why we're seeing such a high performance in terms of volume and injectivity. But I'll still come back to that. So this is the case B2, 101 meter thickness. Permeability had to be increased up to 650 millidarcy to be able to get a bottom pressure buildup that is equivalent to what we have. So either way, we have to tune the permeability data, the permeability parameter, to be able to achieve the same bottom hole pressure that was reported in the data. So that gives us an information about what is possibly going on in the Edwards formation. It's very possible, the trend we saw earlier, lots of fault around this carbonate formation, and it's very possible that this formation has been naturally the permeability of this formation has been naturally induced. So having done for this particular case, this Edwards trend, having done some kind of single phase analysis, it's important to kind of understand how this will perform in terms of when you do the two-phase modeling. So basically, take the lessons from the single phase analysis and plug it into the two-phase analysis. So this again is the result from same Easy tool, but this is the two-phase simulator basically, and you can see using the first case study for the Edwards formation using a thickness of 55 meter and the permeability 1250, that assuming same bottom hole pressure conditions basically, and you can see the capacity we can inject up to 500 megaton of CO2 in this formation, depending on the number of wells you drill, right? And we have capacity on the y-axis. Ideally, you opt to go with the optimal value here. So this is also the second case, which is for the KC2, basically using the permeability of 650 millidalton and a thickness of 101 meter. Assuming the same pressure condition, you can see how the capacity, how much capacity you can get, assuming the same pressure condition. And you can see this is up to 500, between 500 and 550, depending on the number of wells, you decide to drill. So just before I wrap up my talk, we've seen that even for the Edwards formation, there were a lot of really good wells in terms of volume and in terms of injectivity, but there were also some low performing wells, some yellow dots in that trend. So it's there was need to understand why we had those wells, what could be causing those wells to be performing low in terms of injectivity. So to do that, the initial assumption was that this could be as a result of the older wells taking up a lot of pressure space, and then the newer wells are experiencing quicker pressure buildup, limiting their injection. So what I did was to make a plot of injectivity index versus drill depth to be able to see if initial hypothesis is going to apply in this case, and that's proved again to be wrong. You can see there are some low injectivity wells even in the early stages, and we have a well here that is really good in terms of injectivity drilled at a later stage. That kind of tells us that our initial hypothesis that the older wells might be the best performers and the newer wells the worst performers. That's not really the case. So that brings me to some conclusion. The first point I have here is that high performing wells, as we've seen, high performing wells up to 0.8 megatons of CO2 equivalent per year are possible in the Texas Gulf Coast, and this is based on the Edwards trend that I showed earlier. Also, as seen in the Edwards, there is no indication that pressure buildup accumulated by older wells limit the performance of newer wells. Hence, I conclude that observed low performance for this case is not entirely associated with newer wells. Also, observed low performance is likely due to operational issues such as wellbore damage, well design, and equipment failure. And these are issues that for CCS can be easily avoided. The next one I have here is, relating to the Edwards, which is a calcified carbonate. Despite being surrounded by faults, is unlikely to be compartmentalized, which in other words means to have a closed boundary condition. And we also see that it's very likely that it has the result we've gotten so far shows that it has a very high permeability, likely induced naturally by the fault. Also, applying these conditions to any model designed for two-phase analysis enables a more accurate prediction of injection performance for the Edwards formation. And the EZ2 CO2 model, which factors in two-phase flow, estimates up to 500 megatons of CO2 can be stored in the Edwards formation, depending on how many wells a company decides to commit. The Edwards formation provides us with another storage location for carbon capture and storage in the Gulf Coast entirely. Yeah, thank you.
Very interesting work. If people online have questions, you can unmute, but for now, I can start us off. So at the very beginning of your presentation, you had this figure of like the 4,000 wells that you like narrowed down to, and there was like a trend of like the amount of storage that happened over the years, and I would expect it to go all the way up. I don't know if you can bring that plot back up. but it was like from like 1990 or something, and it ended like in 2020. Yeah, it's like way in the beginning.
This.
Yeah, the next one. Why is there a dip in like the 90s to like 2005?
Okay, so this kind of is directly related to the oil production trend. So when you look at the oil production trend, you see similar. In the late 1990s, there was also like a dip in terms of oil production in Texas.
Okay,
Yeah.
okay, huh. And then another one that I had, can you go back a couple of slides actually? Actually, wait, go forward, sorry.
Okay.
It's the one with like the different color dots on the Texas map, kind of like identifying.
Okay. Let's see.
Yeah, so I noticed that for these like high or like the red color ones, they follow along like a specific like southwest to northeast trend. Does that make sense? Or am I tripping? Like you see most of them like here or here. And maybe some up there. Do you know why that is?
Um, there is no particular reason.
Okay.
But one thing I've seen also is that there is some, some of these high, not necessarily the case, but some of these high injection wells, especially up deep, mostly like look, some of them are located close to faults, the major faults, the regional faults in the location. But there is no I mean I really haven't like looked at it in terms of it, there's a trend because it's scattered around,
Yeah.
yeah, because the maybe one thing to mention again is that these are like these are like saltwater injection wells, and some of them may be designed, these yellow ones, they're not necessarily like showing an indication of poor performance. It could be designed for purpose, just to dispose a certain volume here.
Okay. We have a question online. You can unmute yourself.
Hello, can you hear me?
Yes.
Oh, okay. All right, yeah. Thank you for the very interesting talk, Chinemerem. So my question, maybe I missed it in the talk, but I'm just wondering why focusing the analysis on Edwards in particular and not any of the other formations, like Miocene, for example.
Yeah, so for this study I showed, like I have, I'm showing just one case study. So it's the purpose of my research basically to drill down into multiple case studies, right? So I'm showing the result for the Edwards, but there's also results for the Miocene or Oligocene information. So it's one of the key reasons that I'm showing the Edwards because of what I say. It's an area that has not really been explored for CO2 injection. So it's kind of interesting for people to actually start maybe paying attention to the location and see if this location could prove to be a good resource or a storage option for CO2 injection.
I see. Thank you. That makes sense. I also have another question. So I guess the conclusion out of your case study is that pressure interference doesn't seem to be an issue. So is that a general conclusion for all of the formations that you looked at?
No, at least that conclusion is based on the Edwards. If I go to that trend, you can see I have it labeled for, sorry, I think I have a power outage. I think my system went off or something.
Is it like a black screen?
Yeah.
Oh no.
Can you still hear me?
Yeah, I can hear you.
Okay, I'm having a bit of technical issue here, but the plot I showed, which shows like injectivity versus drill date is based on the Edwards. It's only for the Edwards. So it's not like a general conclusion, across the Miocene and Oligocene. And it's kind of understandable because Edwards is a carbonate and it's a voggy formation. So you can get, it's possible to get a good performance in one location and maybe not a good performance in the other location. So it might not necessarily mean that drilling a well at a later stage will be impacted by an injection project that went on earlier.
So does that mean Edwards is a better formation compared to the other ones?
It's a good formation, but not necessarily a better formation. But based on what we've seen, it's one of the top formation alongside the Miocene, Oligocene, Woodbine, and Wilcox. But at this point, to be able to know if it's the best formation or the better formation, and there needs to be a more in-depth analysis into the formation itself.
I see, makes sense. Thank you very much.
Thank you.
Did your laptop come back?
Yeah.
If there's no more questions. Okay, cool. Thanks for presenting. And then you can see probably the recording online if you want to go back and look at it again. So, yeah,
Thank you.
thanks for your presentation.